This is a short video to help you get started with assignment 4, Hubble's law from supernovae. From lectures you've learnt that the universe is expanding and objects in the universe are moving away from us with a recession velocity, a speed, depending on how far away that object is. And that relationship is Hubble's law. So the speed at which an object is moving is related to how far away that object is, and it's related by the Hubble's parameter or Hubble's constant. And in this experiment you are going to be using supernovae or spectra from supernovae to determine how far away those supernovae are and how fast they are moving away from us. So you'll be working out how far away the supernovae is and how fast they're moving away from us. We do this with a number of supernovae with a different set of velocities and distances, and by drawing a straight line comparing velocity and distance, we will be able to work out this value here, Hubble's constant, which will be the slope of a velocity-distance graph. So we're using spectra from supernovae. We're taking light from a supernova, a star which has exploded, and we're putting that light through a spectrograph. We're showing how much light of each wavelength is present from that object. And we get something that looks like this. We get a spectrum. So here we have amount of light, if you like, on the y-axis, and wavelength down the bottom. Now you'll know that if an object is moving away from us, the wavelengths of light, or indeed sound, will be shifted towards longer wavelengths. So here we have a spectrum for an object which we consider to be at rest, not moving relative to us. And we look at the features here and we see a couple of dips. These are absorption lines, which should be familiar to you from lectures. In this assignment we're going to go through a number of type 1a supernovae spectra and look for a pair of absorption lines. A pair of absorption lines correspond to calcium-2 and silicon-2, which is this absorption line here, this dip here, and a fainter absorption line due to silicon-2, which is here. So in each of the type 1a supernovae spectra, we're going to be looking for the same spectral line features. We're going to be looking for a big dip followed by two small peaks. So we're going to look for this shape. We're going to be looking for a big dip and then two small peaks separated by a shallower dip. This is a spectrum considered to be at rest with the observer, so we know what the rest frame wavelength is of this absorption line. It is 3,750 angstroms. We know the rest frame wavelength of this absorption line as well, 4,000 angstroms. When we take a look at the observed spectra of type 1 supernovae, we know that they are going to be moving away from us, and so these features are going to be redshifted. These features are going to appear the same, but they're going to appear at longer wavelengths. The wavelengths will be of a higher value. By comparing the rest frame wavelength with the observed wavelength for these two absorption line features in each of our observed supernovae spectra, we can work out the recession velocity. We can work out how much they're being Doppler shifted, we can work out their redshift, and from that we can work out their recession velocity. So we're going to start off with the velocities first by looking for this feature in each of our observed supernovae spectra. Okay. Now I'm going to go through one of these, this one here, and I have enlarged that just so it's easy for us to see and work with on the video. Alright, so here is our observed supernova spectrum, and remember we're looking for this feature. We're looking for a big dip followed by two small peaks separated by a shallow dip. Okay, well that seems fairly straightforward for this one at least. Here is a big dip followed by two small peaks separated by a shallow dip. Right, how do we record the data from these? So we have a nice table. So where we need to, for the big dip and the shallow dip, write down the observed wavelength for each of those absorption line features. So we're working with supernova O3D1FC. Let's just double check we've got that right. Yep, O3D1FC. Good. Okay. And remember, let's just double check, looking for a big dip, small dip between two peaks. Well, there's the big dip and there's the small dip. Let's go ahead and read off the wavelengths of those observed absorption line features. Okay, so this absorption line lies around about here. Let's work that out a little bit more accurately. So let's see, I think it's around about here. And we can take a look and see where this absorption line lies. Just mark that on our scale as well. I reckon it's around about here. Okay, so the position wavelength of this absorption line is 4,800 and something. Let's work that out as finely as we can. So it seems to be around about 9 millimeters along from a total length of 12 for that division. So let's see, it's 9 divided by 12 times 100 in angstroms, about 75. Okay, so put that in this box here of a table of observed wavelengths for the calcium 2 silicon 2 observed wavelength, and I will just round that up to 4,880. Okay, now we're going to do the same job here for the silicon 2 absorption line, this one here. So it appears at 5,200 and something. Let's see if we can work that out more finely. So that appears around about 8 millimeters out of 12 for that division. 8 millimeters out of 12 times 100 angstroms for the division is about 66. 2/3. I'm going to round that up to 5,270 angstroms, and it's going to mark down here that we're observing these in angstroms. Okay, right. Now we need to work out the redshift of those lines. And the rest frame wavelength for this absorption line, is given in the text, is 3,750 angstroms. I'm just going to write that up here, just to remind me. And the rest frame wavelength for this absorption line is 4,000 angstroms. Now we can use this equation here, given in the assignment. We work out the redshift of the lines by dividing the observed wavelength by the rest frame wavelength and then subtracting 1. So let's do that for this wavelength here. 4,880 divided by 3,750, and we're going to subtract 1 off that, and there's my answer, 0.3. Put that in here, 0.3. And we'll do the same job for this absorption line. 5,270 is the observed wavelength, and we divide it by the rest frame wavelength, which for this line is 4,000 angstroms, and we subtract 1 off that. It gives us that value, and I'm going to round that number up to 0.32. Now these numbers for each of the lines that you observe can be different. That is why we're going to take an average of them, and the average of these two redshifts, and my mean redshift is 0.31. Okay. Now we need to compute the recession velocity. And we do that by multiplying the redshift, our mean redshift, by the speed of light, which is 300,000 kilometers per second. So I take my mean redshift of 0.31 and I multiply it by 300,000 kilometers per second, and that gives me that value there, 9.3 times 10 to the 4, and we're measuring this in kilometers per second. Okay. Now we need to work out how far away the supernova is. And we do that by looking at the apparent magnitude of the supernova, and we have a knowledge of the absolute magnitude of all type 1 supernovae. The absolute magnitude of all type 1 supernovae appears to be the same at minus 19.45. So they all explode with pretty much the same energy. They produce the same amount of light. So since we know how much light they intrinsically throw out, if we observe a type 1 supernovae with a given apparent magnitude, we can work out how far away it is by computing the distance modulus. And this is what we did in assignment 3. So here's the distance modulus here. It is the apparent magnitude minus the absolute magnitude. So when we work out for our supernovae, type 1a supernovae, it will be the apparent magnitude plus 19.45, which is the apparent magnitude minus negative 19.45. So what we need to work out the distance modulus is this value here, the apparent magnitude. The apparent magnitude for each of the supernovae that you're working with is given at the top of each spectra. And here it is here, the magnitude in the blue band is 21.866. So let's work out the distance modulus. It's very straightforward. We just take the apparent magnitude, which is 21.866 for this supernovae, and then add 19.45, and there is our distance modulus of 41.316. Okay, now we need to work out the distance. The distance in parsecs is given here. It is 10 to the power of the distance modulus plus 5, or divided by 5. So we take our distance modulus, we add 5, we divide it by 5, and then we raise 10 to the power of that number. 10 to the power of that number is this value here in parsecs. We want to have our result in megaparsecs, so we divide that value by 1,000,000. And there's my value there in megaparsecs. I'm going to write that down, 1833, and my distance here is in megaparsecs. Right, so that's the complete exercise for the spectra for this supernova. You are going to continue and go through, repeat the steps for all the supernovae that you've been given in the assignment, and you are going to complete this table, working out the distance modulus, the distance, recession velocity. Now some of the spectral absorption lines are easier to see in some of these than others. Give it your best shot. You might get some of them wrong, that's okay. You are going to fit a line of best fit to the data that you get. So you are going to graph the recession velocity against the distance. So on the y-axis you're going to have velocities in kilometers per second, and on the x-axis you're going to have distance. By doing that, you will be computing, you'll be able to figure out the gradient between a velocity distance graph, and that gradient is what you're after in this assignment. It's Hubble's parameter, Hubble's constant. So you take your recession velocities, plot them against distance, find the gradient of that line, and that gradient will be Hubble's constant.